So let's talk a minute about family trees. Here, Jessica is investigating her family tree and she's researching each generation. The first generation is going to start with Jessica. It's just her. And then let's think Jessica has two parents. So she's researching four generations, her parents, her grandparents. I'm going to write G for grandparents. And then her great grandparents. So the four generations, starting with herself. And each generation in my diagram here is a row. So this is what Jessica is looking at, four generations. So here's her. The next row has her parents. The next row has her grandparents. And then up here are her great grandparents. Of course, she has great great grandparents and great 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 grandparents and so on. What we want to think about is the number of parents in each generation. So I'm going to pause the video and let you work with a partner to complete this table and to describe what's going on as we go up Jessica's family tree and look at each generation's parents. You've hit play, so that must mean that you're ready to talk about the patterns that we see in Jessica's family tree. Well, like we said earlier, at first there's just one person in the row. Then our first generation, that's Jessica. And our second row shows Jessica's two parents. Our third row shows her fourth grandparents, and our fourth row shows her 8 great-grandparents. Of course, she also has great-grandparents. There would be 16 of them because each of Jessica's great-grandparents has 2 great-great-grandparents. 8 times 2 is 16. Of course, each of her great-great-great-grandparents has 2 great-great-great-great-grandparents. 16 times 2 is 32. So the family tree is going to double by 2 with each row. And that's what I would say for my description here. Start with 1, multiply by 2, or we could say double. That's how each row changes to the next row. The number of parents in the 5th and 6th generations are 16 and 32. And we can represent that in our table as we have on the left, or we can represent that with a list of values as a number sequence. In the next example, I want you to work with your partner. We have a collection of squares and they are decreasing. Analyze the number of small squares in each figure. So for example, the first one has 49 because it's 7 by 7. Okay, pause the video, set a timer for 5 minutes. The teacher is going to be walking around the room and being sure you're on track. What we want to do is describe the pattern that's going on with these squares. How is the number of small squares changing in each figure? All right, it looks like you're ready to talk about this. Our second square was 6 by 6. 6 squared was 36. First one was 7 squared, wasn't it? Our next one is 5 by 5. 5 squared is 25. And our next one was 4 by 4. 4 squared is 16. So in our table, we have 1, 2, 3, 4. We started with a term value of 49, then 36, then 25, then 16. And if we kept going, oops, hang on. Shouldn't be 3, 2, 1. That should be, I went backwards, 5, 6, 7. We would have, well, you know what? Before I fill in that table, let me draw the figures. We have 3 by 3. 3 squared is 9. It's easier to fill in the table when I have the figures to look at. We have 2 by 2. 2 squared is 4. The last one's actually kind of hard to think about, isn't it? It would just be 1 by 1. And 1 squared is 1. So those are the next terms in our sequence. We could also write this as a list if we wanted to. So these are just our perfect square numbers starting at 49 and working backwards until we get to 1. The omelet question is a good one. This is a real world problem. If you work in a kitchen, you have to know how much food to order, and that's what's going on here with Al's omelets. Al's house of eggs, Nat, makes omelets. Al begins each day with 150 eggs. Let's go ahead and fill that in. The first term is 150. That's where he starts. After making one omelet, he has 144 eggs. After making 2 omelets, he has 138 eggs. After making 3 omelets, he has 132 eggs. Okay, pause the video, and what you're going to do with your partner is figure out what's happening to the eggs. How long, here's a good question. How long would it take Al to run out of eggs? So talk with your partner, describe this pattern, and answer the questions on the left. Pause the video and set a timer for 5 minutes. You've hit play, which means you're ready to talk about this pattern. Oh, look at that. I did it again. Started counting backwards. For some reason, I want to count down instead of up. Well, there we go. Maybe it's because this is a decreasing pattern. Each row subtracts 6. Why is that? It's because Al uses 6 eggs for every omelet. And we could keep on going, couldn't we? At least until Al runs out of eggs. So looking at our pattern, we could write a list: 150, 144, 138, 132, 126, 120, and so on. And what's going on is it is decreasing by 6 because he's using 6 eggs per omelet. Now, I asked you guys a question. Let's see, we already figured out this question as well. The question I asked you guys is I said, how many omelets can Al make? Well, that's actually pretty easy. Just divide 150 by 6, and that's the number of omelets Al can make. Al can make 25 omelets. That's not in the book, though. That's just a Mrs. Johnson question. All right. We are going to skip Donna's daisies. But I do want you to do this troop of triangles. I'm not going to talk about it just yet. I want you just to try it. Let's set a timer this time for 7 minutes. And work with your partner. Figure it out. You can do it. We'll talk about it in 7 minutes. Your teacher will be walking around the room and checking for understanding as you work. Hint, draw a picture first on this one. So here's my drawings. Looks like you guys are ready to talk about this pattern. You probably look a little bit better than mine, but that's okay. There's a lot of different ways to think about this pattern, but let me show you one that makes sense to a lot of people. One way to think about this is to say, okay, we started with one triangle, and then we put 2 triangles underneath it. Then we had 3 black triangles, and we moved those over here, and we put 3 triangles underneath those. Then we had 6 black triangles. So we took those, we moved them over here, and we put 4 triangles under those. So what are we really adding each time? Well, we're really just adding a new bottom row, right? So what's new each time is the bottom row. At least that's one way to think about it. And it makes it pretty obvious to see how the numbers are changing. So first, our bottom row had 1, and then we added 2 to that, and then we added 3 to that, we added 4 to that, we added 5 to that, we added 6 to that. So let's just kind of work this out a little bit. 1 plus 2 is 3. Remember, we started with 3. 3 plus 3 is 6. We started with 6. 6 plus 4 is 10. We started with 10. 10 plus 5 is 15. We started with 15. 15 plus 6 is 21. So that's one way to think about how the number of dark triangles here is changing. So we started with 1, and then we had 3. Our next triangle had 6, then 10, 15, and 21. And what's going on is we added 2, we added 3, we added 4, we added 5, we added 6. What would we add next? You got it, 7. So this row would be 28 if we wanted to keep on going. It's not hard, right? We could draw even more figures if we wanted to. So to represent the number of dark triangles, let's see, we did a table of values. We could also, if we wanted to, make a list. So show a numeric sequence using a list of numbers. There we go. And I'm going to do dot, 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 because this could keep on going, couldn't it? All right. We are, for this one, looking at another real world example. This time it's a gamer. Mike is trying to beat his high score on his favorite video game, and he unlocks some special mini games. Before playing the mini games, he has 500 points. So that's where he started. That's the first term in this sequence. After playing one minigame, he has 550 points. After playing two minigames, he has 600 points. After playing three minigames, he has 650 points. I'm going to add another row to this table. So think about the total number of points that he's gaining from the minigames. Describe the pattern. Well, let's just do this one together really quick. It's easy, right? He's adding 50 points each time. Each minigame is worth 50 points. So it's increasing by 50. After 5 minigames, he should have, oops, didn't mean to slide that over. After 5 minigames, he should have 700 points. And after 6 minigames, he should have 750 points. There we go. So the next two numbers would be 700 and 750. And we could represent that with a table or with a list. This is a real world sequence. He starts with 500 and it increases 50 points for each game. We are going to skip the polygon party. And I want you to look at the pizza contest with your friend. So work with your partner, and let me just tell you what's going on real quick. Jacob is participating in a pizza making contest. Each contestant has to bake the largest and most delicious pizza that they can. Jacob's pizza has a 6-foot diameter. After the contest, he plans to cut the pizza so that he can pass out slices to share, because he's not about to eat a pizza with a 6-foot diameter. He begins with one whole pizza like that. And then he cuts it in half. And then he cuts those slices in half. And then he cuts those slices in half. And then he keeps going. He keeps on cutting the slices in half. So first he has one big slice. Then he has 2 slices. Then he has 4 slices. Then he has 8 slices. Then he has 16 slices, and so on. The pattern. This is the pattern that describes the number of slices. One big slice, which he cuts in half to make 2, which he cuts in half to make 4, which he cuts in half to make 8, 16, and then 32. And I think that's where he stops, maybe. Maybe he makes more, I'm not sure. But he cuts it in half, and his number of slices is doubling. So I told you that because the question this is asking you is a little different. It says to think about the size of each slice in relation to the whole pizza. So our first one, it was one slice out of one whole, so one whole. Our next one, he had, each slice would be 1 out of 2. For the next one, each slice would be 1 out of 4, and so on. Pause the video for about 2 minutes and talk about this with your partner. What's going on in this sequence? All right, you've hit play, which means you've had time to talk about this problem, about what's going on with this pizza. Remember, we started out with 1 slice out of 1 whole pizza. Then we had 2 slices, so each slice was half the pizza. Then we had 4 slices, so each slice was 1/4 of the pizza. Then we had 8 slices, so each slice was 1/8 of the pizza. Then 1/16, and then 1/32. If you cut those in half, they would be 1/64. But we're going to stop there. And what's the pattern here? It's dividing by 2 each time, right? Or you could say multiplying by 1/2. Let me write it both ways. Dividing by 2. Makes sense because he's slicing it in half each time. We could also say, because it's the same thing as dividing by 2, multiplying by 1/2. Multiplying by 1/2 is the same thing as dividing by 2. So determine the size of each slice compared to the whole pizza after the next 2 cuts. Well, there, I did that right there. I just made a list. I guess I should actually draw an arrow for this one too. And then we can use this list to complete our table. So we have 1, 1/2, 1/4, 1/8, 1/16, and 1/32. And we could easily keep going if we wanted to. And all we're doing is multiplying by 1/2 each roll. Or cutting it in half more, right? Let's look at coin collecting. I'm actually not going to talk about this one with you. I'm going to let you do this on your own. But what's going on is Miranda's uncle collects rare coins. He recently purchased a rare coin that he believes is worth $5. He claims, this is what he thinks, the value of the coin will triple each year. Triple means to multiply by 3. So even though the coin is currently worth $5, he believes it will be worth 15 next year. So it started here. This is where it will be next year. He thinks in 2 years it will be 45, and in 3 years it will be worth 135. So that was nice of him. He gave us the first 4 terms of the sequence already. Your job with your partner is to figure out the value of the coin after 4 and 5 years, which are actually going to be the 5th and 6th terms of our sequence, and to represent the value of the coin after each of the first 5 years as a numeric sequence and in the table. This is the end of this video, but you have 4 minutes to work on this task with your partner, and your teacher will be checking for understanding as you work.